And we're live from Berkeley, California, and welcome to Dark Matter Day. My name is Dan McKinsey. I'm a professor of physics at UC University of California, Berkeley, and a faculty senior scientist at Lawrence Berkeley National Laboratory. And I'll be talking about dark matter and some experiments that use liquefied noble gases to search for its interactions with ordinary matter. So there's evidence for dark matter from a variety of different length and time scales in the universe, from the Big Bang, where the speckle patterns of the cosmic microwave background give us evidence for dark matter, to the formation of galaxies and the rate of their formation, to microwave, to lensing of light around galaxy clusters. And all this evidence over many different length and time scales tells us that about a quarter of the mass energy density of the universe is dark matter. So one piece of evidence is seen from looking at the rotation curves of galaxies. That is, if you look at the rate that galaxies are rotating and look at the velocity of stars as a function of distance, that is relatively flat at large distances instead of dropping to slower velocities as you go out further. And that's a sign that there's all this dark matter material holding the galaxy together and allowing those stars to move around quickly around the galaxy. And this was discovered by Vera Rubin collaborators in the 1970s and 1980s. So you can see how observations have high velocities at large distances, whereas this is what you would expect if you only had the visible matter up there to look at. Now there's various ways you could think about, instead of having dark matter, having some kind of modified gravity, but all the evidence on very different length scales in the universe basically makes it very difficult to come up with a modified version of gravity that allows you to explain our observations. So you could think about maybe this gravity different, changes in gravity allows us to fit the data, but it actually is quite difficult. And dark matter becomes a very simple explanation for all the observations we see. Another example is gravitational lensing. So if you have visible things in the background, the light from those, due to gravity, gets distorted, and so you can actually see distorted images and rings here on Earth of different objects. And as a result, you can work out what in the intermediate space is causing that light to bend and its distribution in mass. In fact, there are cases where most of the mass causing the lensing is actually at a different place than most of the ordinary matter from ordinary gas. So here's one example called the bullet cluster, where if you image the dark matter and its gravitational potential, it's actually separated in two places compared to most of the ordinary matter, which is entrained in the middle after these two galaxies have collided. So here's an example. If you have two of these galaxy clusters colliding, then the ordinary matter gets entrained in the middle, and the dark matter in blue here comes off both sides. So we actually have examples where dark matter is physically separated from the ordinary matter. Now, we don't know what dark matter is. There are lots of ideas called neutralinos or axions or gravitinos, or dark neutrons, dark electrons, all sorts of possibilities for what the dark matter could be. But we do know that it's a different kind of particle than we have from visible matter, quarks and protons and neutrons and neutrinos and photons. We know it's some kind of new particle. So one way we can look for dark matter is actually trying to see its interactions with ordinary matter. And a number of experiments, we're looking for a kind of particle called the WIMP, or the weakly interacting massive particle. And the idea is that a WIMP will occasionally bump into atomic nuclei. And this is a very rare process. Maybe a few times a year you might look like this in one of your detectors. And so we build very, very sensitive detectors that go deep underground to get away from radioactivity and are inside lots of layers of shielding to keep a very quiet environment for looking for these interactions. So one of our favorite materials for this is liquid xenon. Liquid xenon is the heaviest of the stable noble gases, and in the LZ experiment I'll tell you about, we'll have about 10 tons of liquid xenon in it. And also, we've been using it in the LUX dark matter experiment. Detector, dark matter particle comes in, and it makes the liquid xenon emit light, and it also emits electrons, and those electrons are detected. And we see two signals for every scattering event. And this allows us to tell us about the kind of interaction that happened in the liquid xenon, as well as the detailed position information and energy information about the events in the liquid xenon. Here are some photos of the LUX detector, which we built and operated for several years at the Sanford Underground Research Facility in South Dakota. You can get an idea for the picture, the size of it. It's in line with Teflon in the inside surface. Lots of ultra low background materials like copper and titanium were used in its construction. Here's where the experiment happened. It's in the Davis campus of the Sanford Underground Research Facility, about a mile underground in the Black Hills of South Dakota, in this sophisticated facility for very low back. Here it is, a photo of the place where it is in South Dakota, in the beautiful Black Hills. And at the end of the running of the experiment, we basically were able to rule out cross-sections for dark matter that were especially large, and for dark matter particles that were relatively large in mass. So if you think about this unicorn as your hypothetical dark matter particle, we can rule out that the unicorns had masses higher than some amount with a cross-section or a size above some amount. And so we can keep doing more experiments to further explore this dark matter parameter space. From LUX, if you're ever visiting the we're going from this scale LUX to a bigger and better version called the LUX-ZEPLIN experiment. ZEPLIN design is sensitive to LUX than LUX. It's about halfway built. We'll start commissioning it next year. Here's some photos of the parts of LUX of LZ coming together. Here's the titanium cryostat that's been built for the LZ experiment, the photomultiplier tube arrangements, the xenon that we need to run the experiment, grids, a high voltage delivery system, lots of high-tech pieces that come into the apparatus. At Berkeley, we're building the cathode high voltage delivery system where that high voltage. Another interesting liquid we're starting to study is superfluid helium. That might be able to look for especially light or low mass unicorns on our picture before. Superfluid helium has amazing properties, has no viscosity, it can climb walls, it has quantum turbulence. Very special detector material. Has long-lived excitations that can propagate long distances and detect tiny energy depositions from the dark matter, including scintillation light, triplet molecules that are produced, as well as phonons and rotons, special heat particles that pass through the liquid helium. And we're doing some R&D, building these new devices to start looking for these small interactions in liquid helium and developing the technology to look for lower mass dark matter particles. Is there dark matter on Earth? That's a great question. So the idea is that dark matter is all around us. Even if you're deep underground or at the surface, there's dark matter particles going through you all the time. And that's because the dark matter interacts very, very weakly. It doesn't interact much with ordinary matter. So it doesn't care. It doesn't really get blocked by the Earth in any way. And it's around us all the time. And the question is, could dark matter block different particles? And yes, it could. So we usually think about it in a sort of a simple way of thinking about it as one particle, but could be many different kinds of particles. One particle that's a lot like dark matter is the neutrino. So the neutrino particle those are produced in the sun in enormous quantities, and we detect them routinely now. They were first detected in the 1950s, but now we know how to detect them very well and have measured their properties. The neutrino can't be much of the dark matter. The neutrino particles are too light, as far as we know. But like the dark matter, neutrinos are all around us all the time. They don't care much about going through the Earth. And so the dark matter, if it's a particle like the neutrino in that it interacts very weakly, could sort of qualitatively be a similar particle except heavier.
Hi, so I'm Matt, and I'm a professor at Berkeley, and also I'm affiliated here at LBL. And I'm going to talk about searching for dark matter by looking for vibrations in crystals, and also potentially in superfluid helium with Dan. So I want to go a little bit more into that plot that Dan just showed with unicorns, so we can really understand the challenges of this next generation of experiments. So this is what we've already explored, this area of higher mass dark matter candidates with large interactions. So interaction is on the y-axis, and mass is on the x-axis. And LZ, Dan just told you about, is going to push down to lower interaction strength between us and dark matter. And to do this, we're going to make LZ bigger. So this is why LZ is a 10-ton experiment. And it's this huge challenge. By contrast, I was still on this last slide. By contrast, for super CDMS, my experiment, we're trying to push down to lower masses. And one of the things you see is all of these curves. If you see this LZ curve going here, and you see the curve of LUX and the curve of super CDMS sensitivity, they're all going up very quickly. So they all lose sensitivity to lighter mass dark matter. So it really comes down to just kinematics. And you can do this actually at home if you have a bouncy ball. Just toss a ball against the wall, and you don't give a huge amount of energy to the wall. The wall doesn't fly away from you. And this is because there's a kinematic mismatch between the dark matter, or between the bouncy ball and the wall. And for our experiments, the wall is basically this large nucleus, and the dark matter is this very small light mass particle. And it turns out that the energy, the vibrational energy given to the nucleus, scales as the dark matter mass squared. So it's going to be, if you have a large dark matter candidate like LZ is looking for, you're going to have a small but currently measurable amount of energy that you can look at. By contrast, if the energy is if the dark matter mass is on the scale of a proton, so if the dark matter has the mass of a proton roughly, so for you to understand how small 10 to the minus 17 joules is, we can do like a few things. So imagine taking a paper clip and lifting it up a femtometer. So that's 10 to the minus 15 meters. That's 10 to the minus 17 joules. Another one you can think of is this is the amount of random kinetic energy. So everything in the world, we're at room temperature. And if you think about it on a microscopic scale, everything is vibrating a little bit. And 10 to the minus 17 joules is the amount of energy that 1,000 atoms have in their vibrations. And just to set the scale of how small 1,000 atoms is, one human cell has 10 to the 14 atoms. So this is just a really small. So the question is, how can we do this? So my group works is we try to build very sensitive calorimeters. And at the core level, you can think of this just as a pot of water and a thermometer. So the idea would be dark matter comes in, scatters, leaves a little bit of energy, and then we measure it with a thermometer. Of course, this is going to be a really bad calorimeter because that thermometer is not going to be very sensitive. So let's actually go this next step and ask how can we make that idea way more sensitive than it currently is. And so the first thing we have to think about is we're trying to see this little red arrow, which was dark matter scattering off of this atom and giving us that very small 10 to the minus 17 joules. And at room temperature, we already talked about this. All of these atoms are vibrating around just randomly. So there will be no way for us to ever see that small vibrational energy if all these atoms have random vibrations at room temperature. So the solution is we're going to go and put our detectors, our calorimeter, in a refrigerator that takes us very near absolute zero. So roughly it takes us to 10 milK above absolute zero, which we think of in Fahrenheit as minus 409.66 degrees Fahrenheit. So, and you can see the refrigerator here. It's a little bit more complex than your refrigerator at home. But, you know, and many of the principles are actually very similar in how they work. So, next slide. So the next thing we have to do is we have to fabricate the calorimeter. So the standard material that my group uses is we use large, and in the future, smaller crystals of pure crystals of right now germanium and silicon. So there's about 1 kilogram single crystal. And then we're going to fabricate these very sensitive superconducting thermometers all on the surface. And you can see these thermometers right there. They're those little tiny ovals. And when dark matter comes in, which I show right here, dark matter comes in, hits, it makes vibrations. Those vibrations bounce around in the crystal. And eventually they get absorbed in this thermometer. And we see the signal. We just read out that signal. So one can say if we're sensitive to dark matter, that very small vibration from dark matter, the bad thing is we're sensitive to everything. So unfortunately, if you're in my lab right now and you clap your hands, we can see that. It pops our detector up and we're like, uh-oh. So this is one of the things that we're working on is actually decoupling our detectors further from the environment and the vibrations of the environment. Of course, you can think of these things are in refrigerators, and your refrigerator shakes a little bit, compressors and other things in that. That's definitely a problem. We have our compressors isolated, we spring load them, and we still see a little bit of noise from there that we're also right now in the process of getting rid of. Finally, my lab is right across the hall from this giant classroom of all these students coming out every hour, and you immediately see them pop on their cell phones, and we can see that as well. We've made great progress actually recently on suppressing these signals, so I can confidently say this one we've totally solved. And anyway, so that's the thing. The final step, of course, is to go underground and search for dark matter. So in some sense, it's very similar to Dan's experiment that he talked about. We want to go underground, get rid of all these outer space backgrounds. And so Super CDMS will start taking data at Snow Lab in 2021. For this large-scale experiment that I was talking about to search for masses between 1 GeV and 10 GeV. And then, so that was this. But these same ideas and that same philosophy of why is it so hard to search down in this range to lower masses, it just keeps on going. You have to make, if you want to search for lower mass dark matter, you must make. And actually with LBL, we're thinking about how to do this. And we're not talking about kilogram-sized single crystals. We're talking about 1 centimeter cubed, or we're talking about centimeters squared. So that's it. Thanks so much. Can gravitational waves help to explain dark matter? So there are actually a few theories of how dark matter could actually be seen with gravitational waves. So one is that it's a different type of dark matter, and it's some kind of axions or some very light dark matter particles. So on that plot we just showed, it would be way over here. And that dark matter is coalescing around black. Therefore, you'll be able to see the signature of this dark matter in gravitational waves off of those black holes. So that's actually one exciting way where we could use gravitational waves. Let's see. So that was Facebook. OK, so the next question was, it was something. Oh, thanks. What's the difference between dark matter and dark energy? No, that's also another great question. So dark matter is massive and cold. That Dan showed, that dark matter is what is in galaxies and clumps. So dark energy in some sense is exactly opposite. It's not clumping at all. It's just everywhere. And it's pushing us apart, not pulling us together. If we could see dark matter around our galaxy, what shape do scientists think it would be in? Actually, we can see dark matter around our galaxy and how it looks. And Dan actually showed a picture of some halos. So here, this is actually a simulation here of a simulation of dark matter from the early universe and how dark matter starts to clump and produce and starts to go into small galaxy-like sizes. But also, we've done simulations of dark matter on the galactic scale too. And so we have excellent simulations on all scales. And we've also started to look at trying to map dark matter throughout the entire galaxy as well.
Hello, my name is Simone Pagan-Griso. I'm a staff scientist at Berkeley National Lab. And today I will tell you actually a bit of a different way in which we look for dark matter as well. And in particular, how we look for it at the Large Hadron Collider. So the Large Hadron Collider is actually the highest energy particle accelerator we have to date. And it's located in Geneva, Switzerland. You can see a picture here. The collider is actually underground, but you can see the yellow line here to show you where it is, and it has a length of 27 kilometers. It has several facilities, and it has so-called different experiments that try to detect these collisions. The one I work on in particular is called the ATLAS experiment. It's located here near the heart of the CERN laboratories. So one thing I want to point out is that to make such large accelerator and be able to make measurements with that, it requires a large collaborative effort. And in fact, this is a collaboration that spans the whole world. We are more than 3,000 scientists working on this experiment from about 180 institutions around the world, spanning 38 countries. You can see this picture highlighted in yellow all the countries that participate to the experiment. So this is really not a few scientists' effort, but it's actually the biggest collaborative effort ever attempted in science. Similarly, the actual physics program, the measurements that we perform using this accelerator is a quite vast measurement program. We don't only look for dark matter, we look for many different things. In particular, one thing we like to test is a theory we have, the so-called standard model of elementary particle or particle physics, which is a theory that tries to explain essentially at the fundamental level every phenomena that we see around. So here you have a sketch of what we think are the fundamental particles in nature. So we have most of the matter we know is really composed by just a few of them, the up and down quarks and electrons, and that is enough to build atoms and basically most of the matter around. But we know that this is not the whole story. And in fact, in extreme environment, either deep in space or in our laboratories, we can recreate basically all of these particles that you see here are more exotic form of matter, as well as different particles that are the mediator of forces. And the last addition actually to this collection is the so-called Higgs boson that was only relatively recently discovered in 2012, produced at the Large Hadron Collider for the first time, and then resulted in actually a Nobel Prize to Englert and Higgs following this experimental discovery after they theorized this particle. And in fact, if you want to know more about the Large Hadron Collider, I invite you can check out these links. Atlas.ch is the website of the experiment. It has a lot of information about the experiment, and Particle Adventure is a very nice website that was started by the Berkeley National Lab, which has a lot of information about what is standard model and so on. So now let me go on and tell you a little bit now, how do we look for dark matter? Well, dark matter, one thing we know of dark matter that is none of the particles I showed in the last slide. So if dark matter must be something different that we haven't seen before. We have ruled out basically that any of the existing particles can account for dark matter. So this is a sketch of what Matt and Dennis have basically showed you already. So you can try to detect dark matter from its interaction with ordinary matter and try to look at essentially the effect of this bouncing around of dark matter through ordinary matter. At the Large Hadron Collider, we do something different. We try to look at it in a different way. So the next slide, you can see the way we do it is that instead we take ordinary matter, and in particular we take protons, and we make them collide together. Now, we make them collide together at very, very high energies. and high energy can be transformed through some specific interactions to mass to create new particles which have different masses. And this is how we try to create in laboratory dark matter candidates. So this is fundamentally different from the previous approaches where you try to detect dark matter that is around through weak interaction that it may have with ordinary matter. Here, instead, we try to take ordinary matter and, in some sense, transform it through the same or similar weak interaction into a new dark matter particle that would be created in laboratory and try to detect them. So how we do that, we start from protons, so basically hydrogen atoms stripped off of the electron, and we accelerate them through various stages of these accelerators. And this is a very large complex, and in fact, the Large Hadron Collider is only the last stage, this last ring of 27 kilometers, where protons fly underground into this tunnel and get accelerated. And there are high electric field that accelerate these protons and big magnets throughout the ring that allow you to keep your protons inside the ring. So in this animation, you see a single proton accelerator. Practically, we accelerate hundreds of billions of protons at a time. And these, in specific parts of the ring, they actually collide. We make them collide only specific parts of the ring. And they transform into a variety of known particles and, we hope, unknown particles that we'll be able to detect for the first time that interact with our detectors, that act as a sort of giant cameras that allow us to record and understand what is going on. So in this example, for instance, you see a variety of particles being produced with these white lines and 4 particular type of particles we call muons that were produced, identified by our detector. And you see in the various colors how the various detectors react to this particular interaction. So in reality, this animation shows you one particular collision. But given the interactions that we are looking for are very weak, we need to actually repeat this experiment multiple times. We have about 50 million collisions happening every second. We started taking data in 2010, and we are scheduled to take data all the way to up to about 2035. So we will be able to collect many, many, many collisions. And this is a key to be able to look for rare phenomena. So let me show you a little bit more about the detector. So what we use to record this collision, to know what happens. And this is a cartoon of the ATLAS detector. And the reason I show you is to show that this detector, this collision happen at very high energy, and you need a very big detector to be able to measure them accurately and contain them. So this ATLAS detector is 25 meters tall and about 44 meters wide. Be careful, you see two pictures, the cartoon of 2 people depicted there just for scale, and you can see these different arrows pointing to different parts of the detector. And why do we need very different parts of the detector is because different known particles interact with. So in the next slide, thanks, Glenn, you can see a cartoon showing that. So here you have few type of particles that we know about, that are well measured, that can be produced in these collisions. And each of them interacts in a different way with our parts of the detectors. Here you have a sketch of different parts of the detectors, the so-called tracking part, which looks for charged particles, the calorimeter that tries to stop some particle and measure their energy, and a muon system that tries to look specifically for muons that we expect to interact very lightly with the rest of our detector. And on the far right, you see a particular particle, for instance, neutrinos, which have been already mentioned by Matt, which we expect to interact very, very weakly to our detector, similarly to what we expect dark matter to do if it is producing this collision, and leave our detector actually undetected. So given this dark matter, if it is produced as neutrinos, will not interact directly with our detector, obviously the question is, how can you say that dark matter was produced? And in fact, the way we do it, we take advantage of energy conservation. So in the last slide, I want to show you an example of this. So this is a transverse view of our detector. So protons arrive from the two sides of the screen and collide in the middle. And here again, you can see an example of the products of these collisions. And you see with the different colors, a very high energetic set of particles produced in one direction, and a lack of such energy in the other direction, which I depicted with this big yellow arrow. So we expect energy to be conserved, so everything that goes in needs to go out. And so looking at balancing the energy in the collision we observe, we can see that something is missing on one side of the detector. Now, as I said, this could be neutrinos, but could also be dark matter. The good thing is that we know how many neutrinos we expect to produce, so we can look at many of these collisions and see if the number of collisions we observe of this type is compatible with what expected from neutrinos, or something more shows up. That could be a direct test of dark matter, direct detection of dark matter. And I will actually stop on the last slide and take questions from there. Okay, so from Harry on Facebook, how could the discovery of dark matter change our understanding of physics? Yes, that's a very good question. So actually, can I, Glenn, can we go back to one of the slides on the back, not forward? Yes, to the standard model chart. So, yeah, that's perfect. So the reason the discovery of dark matter can change our understanding is that there is any of the particle known. And this is our most complete theory that has been tested until now to round. So discovering dark matter would put a new piece here. Where this piece question, you cannot just, in this theory, we cannot just add an additional particle and call it a success. And in most of the theory that try to explain dark matter, in fact, dark matter doesn't come alone. It will come with a plethora of different other particles, which I used to explain it. And so it will change our understanding in the sense that dark matter will likely also add a significant amount of other particles that we can hunt for and can change our understanding of the different interactions work. It may hint to new interactions. It depends really how it will look like when it is discovered. So we have another question. How fast are dark matter particles estimated to travel in kilometers per hour? So that depends on their mass, which we actually don't know. In most of that we look for, they actually produce in this LHC collision, they're expected to travel very close to the speed of light. As actually most of the particles I've shown you in this simulation, they basically get produced with energy that they travel very close to the speed of light, down to maybe from half of the speed of light all the way to very close to the speed of light. So does the graviton relate to dark matter at all? That's a good question, and no, it's unlikely to essentially relate. There are a quite big set of reasons for that. So, but let me stress that graviton itself is a sort of a particle. Similarly, in this sketch, you can see the gluon, photon, Z and W bosons. These are the so-called mediator particles that mediate forces that are electromagnetic forces, strong electroweak forces. The graviton is supposed to be a particle gravitational force. Unfortunately, it's really, really hard to detect, and in fact, we haven't detected it in any experiment. So we have another question from Facebook, from Hong Kong. Hello, thanks for connecting. Do we know where is the highest concentration of dark matter in our solar system? So yes, we have, as we've seen images of simulations, we know how dark matter kind of clusters together. We have at least a good idea of it. So we can estimate where we do expect larger concentrations of dark matter. We can't rule out there are other places where we may have a higher concentration that we haven't observed yet, but we have a good idea, gravitationally speaking, how dark matter interacts. So these allow us to predict where we expect that. Could dark matter particles have antiparticles? This is a wonderful question. Thanks for asking. Absolutely, yes. They will. We do expect. We don't know what the dark matter particle is, but in all our expectation, a particle will have its antiparticle, and this includes the dark matter as well. If now this will be two distinct particles or not, we'll have to see. Will depends on the nature of dark matter, but we do expect, yes, to have a corresponding antiparticle. From Facebook, Karim, can dark matter radiate light like ordinary matter? So it's actually why the dark matter is called dark is because by itself it doesn't emit light like the it doesn't. There may be cases where some light is emitted, and it's one way that people have been looking for dark matter, but these are pretty rare cases, and it all depends strongly on the nature of dark matter. There's some model that may predict that to happen in some circumstances only. Okay. All right. Thank you very much, everyone, for connecting then. It's been a pleasure to walk you through these different experiments and how we look for dark matter. And I think we are heading off to Genova, Italy, next. And if you want to know more, I invite you to go to darkmatterday.com for more. And again, thank you very much for connecting.